everybody. I'm Thomas, Zurbuchen, and I'm so glad to be closing off this conference. I know I'm between you and beer, I'm told, so I'm going to make sure that I stay exactly on time. And what I want to talk about is stories of two missions. One that I would call is the mission of my lifetime, Voyager, and the other one is the James Webb Space Telescope, which I think is the mission of my children's lifetime. And I want to talk about the transition of those missions from a data-poor mission that nonetheless has been really inspirational and has transformed our understanding of nature to a data-driven exploration. I want to close off and kind of tell you what's happening now. And the point I'm going to make that way over half of the new research results come from not analyzing new data, but all the data. All the old data in a way that was not possible before. Frankly, that ratio is increasing. So much of the research is enabled by cloud, by AI, by other technologies that you're working on. This is a picture of a time where I was 4 years old. Early 70s, a mission was put together by a bunch of engineers here. What you see on top is an antenna that's going to be important later in the story. It's you see immediately, this is a really kind of handmade and kind of improvised thing. What was so special about this mission is the mission was basically quite simple. It's a massive antenna, 3.7 meters, a high-gain antenna, and there's a bunch of instruments hanging from it. You see at the bottom right there, something that looks like a big tube. That's the battery. It's a nuclear battery, so it's just nuclear material that is decaying, that's warming the environment, and because of that warmth, it drives electricity and powers the whole spacecraft. And the rest, basically, is just instruments that are hanging from it. And what this spacecraft, actually two of them, what they were supposed to do is explore our solar system beyond what we had seen. What we had seen to that time, kind of early 70s, is of course the Earth. We had seen Mars, we'd seen Venus, and for the first time, just before, we'd flown really quickly by Jupiter and nothing else we'd seen up close. Every image that we had of planets out there, of moons, was from the ground, with telescopes, of course, that have the challenges that come from the ground. In 1978, this happened. 77, this happened.
In the late summer of 1977, two unmanned spacecraft, Voyager 1 and 2, lifted off from Cape Canaveral atop Titan Centaur rockets. Traveling uninterrupted through interstellar space, the Voyagers will endure forever, long after everything man has ever built has crumbled into dust. In the event the spacecraft encounter alien intelligence, both Voyagers carry a copper phonograph record, a message, celebrating the sights and sounds of Earth.
And friendly wishes.
These unique discs contain photographs of everyday life, as well as voices, offering greetings in 55 languages. There are also animal noises, the music of Beethoven and Chuck Berry, a baby crying, laughter, rain, and a heartbeat. All of the planets in Voyager's path were in perfect alignment, something that occurs only once every 176 years. The spacecraft were in position to visit all 4 of the outer planets, a grand slam, an interplanetary home run.
It was an absolutely amazing time. What actually happened, because of the alignment of the spacecraft, the time of launch was set within a 4-month period. And what happened is there's a couple of instruments that were struggling, and the electronics boards that were flying were the test boards from the lab with like hand-soldered things and wires hanging off it because the flight thing had a problem, and they just slapped it on and left. And so what I want to show you is this kind of ambitious mission, again, using the alignment to kind of Jupiter to kick the spacecraft out into the outer solar system and actually deflect it so that every planet could be seen. And I'm going to show you just a few images that are meaningful to me. This is one of course, it shows Saturn with its very thin razor blade thin rings. The one thing we learned in the meantime, not from Voyager, is that 300 billion years ago, when dinosaurs started roaming on Earth, there were no such rings. So the rings are quite recent if you're looking at the age of the universe. We saw those rings, the structure of them, triggering a whole set of theories of failed moons that collided with each other. This is Neptune, the outermost planet, a planet that actually was discovered because of predictions that were made because of perturbations with Uranus. Basically said there should be a planet there. What is it? And basically, just by simple calculations on a board, this planet was predicted, observed, and 17 days after that, this body was observed. This is from the flyby of Voyager. This is the moon of Neptune called Triton. And you basically see the intricate details. You see kind of the carvings almost on there. You see some impact craters that are there. You're looking at this. Of course, what I'm showing you is data. At the end, I'll tell you how much data. And so I'm trying to amaze you because look at the amazing detail that this flyover does. It's only stitched together images from the spacecraft. By the way, the one thing that was also discovered, this is another view of it with spectral data. Do you see these brownish or kind of dark patterns that are at the bottom? They're visible, kind of like spots of Triton. Those are geysers and massive storms of the surface of Triton. In fact, record-setting, nowhere in the solar system are these phenomena as strong. My favorite image is from Valentine's Day 1990, where Voyager, after passing by all these planets, turned around and took a picture back. 6 billion kilometers. 6 billion kilometers back there in that beam of light is our own planet. It's the best view of ourselves from the farthest away we've ever taken a picture. So you're on there if you're as old as me. Born after 1990, you're on there. It's part of that pixel. It's, of course, the poetic, the poetry that was given by Carl Sagan, talking about that. You know, all our history is in that beam of light, on that pixel in that beam of light. All of our future is there, and we want to cherish it. So for me, this is just an amazing thing, again, coming back. So how did that work? So here's many of you are technical, so let's turn technical. This is the Voyager compute capability. The data computer is actually, there's not actual computer because it was built before the CMOS chips and microchips. It's just a 16-bit processor, 3 processors that work next to each other, each one of them fully redundant. By the way, in the meantime, only 1 copy works of each. The last duplicative just failed a few weeks ago of one of these spacecraft. In all the other, they're already on the 2nd string. And so there's a processor for the orbit. That's pretty important, by the way, because what you want to know is where is the Earth? Because when you get lost, what you want the spacecraft to do is turn the antenna to the Earth and wait. And if you don't do that, you lost the spacecraft forever. So that chip worked really well. Then all the instruments, all the science instruments, all the data, all the images I just showed you come through that and then compute for the guidance, navigation, and control, right? Kind of the helping basically the spacecraft to operate. It's energy storage, it's energy management, and so forth. The total memory is 70 kilobytes. And if you look at right now, just as of 2 weeks ago, roughly, we're at 166.4 Sun-Earth distances right now. And if I take a beam of light or a radio transmission, and I basically go to Voyager 1, it takes 23 hours. So if I'm telling Voyager 1, how are you doing? I go to sleep, go to sleep again, because the thing goes up there. Voyager says, I'm fine, sends it back another 23 hours. And so after twice 23 hours, it says, I'm fine. So fixing problems is really hard, is my point. So just very few times you can go back and forth, and you never want an intermediate state. So kind of like the trick is to really be accurate and simple. Voyager 2 is just behind it at 19.3 hours and the equivalent distance. The bit rate now is 120 bits per second. The bit rate is largely 1 over r squared. It's a little bit less than 1 over r squared because the energy, remember how I told you it's a radioactive battery? The radioactive battery actually has less power because the radioactivity drops. And so there's less power, and there's 1 over r squared for the distance. So kind of the order of magnitude of everything I showed you, all the images were of the order single-digit kilobits per second. That basically everything we know about Neptune, about Triton, about the storms, the geysers, everything came from that. At the beginning, there was a data recorder, basically a tape that was basically when the spacecraft was measuring, it could put something like 12 hours of data on there, and then you could play it back. In the meantime, both spacecraft only work. We only know what they're measuring because, so to say, fork to mouth. So they measure and immediately send it down to the Earth. So if we're not watching with our 70-meter antenna, we're not seeing what Voyager sees. So that's my point is it's the simplest system, absolutely ingenious, and has transformed. Every school, every book about planets in the entire world has the images that I showed you. If somebody wants a Neptune image, that's it. It's kind of embarrassing. We haven't gone back. So there. Uranus also. So that's basically it. I'm going to tell you now about the other spacecraft, kind of, as I say, the next generation spacecraft. This is very much bigger. I showed you the antenna is 3.5 meters or so of Voyager. The mirror here is 6.5 meters, and it's made basically with gold color, because what we want to do is have infrared reflect of it. It has to be cool, because what we want to use this for is an eye into the early universe, the deep infrared early universe. The only thing we can do that is have a huge telescope and have a very cold telescope. The way we make it cold is by having 5 of these heat shields that are always pointed towards the sun and the Earth. So we're on the same side. It's basically 1.5 million kilometers towards midnight, if you want. So if the sun is exactly on the other side, 1.5 million kilometers away from the Earth, is this spacecraft with the heat shield, if you could see it from Earth, the heat shield pointing in this direction. That heat shield is the area of a tennis court. So it's a much more complicated, much bigger thing. And here's the compute capability here. By the way, it's not super impressive either. The processor, the way, for example, SpaceX launches their rockets is with much more advanced computers. And the reason this one uses the RAD 750, which is basically a PowerPC analog, is because it's built such that it doesn't have any radiation impact back there. There's a lot of radioactive radiation from the galaxy that is hitting there. The memory is 68 gigabytes, and I told you already where the location is, 5 seconds for the light. So it's a lot. I mean, you still can't joystick it. And if something happens, it needs to know what to do, just like Voyager. And by the way, things do happen. I think we lost the spacecraft the first week. We lost it 3 times. So my point is that don't think it all. At the end, the story is always about perfection, but that's not how it really works. So the bit rate is 28 megabits per second, and once decompressed, it's something like 235 gigabytes per day. And so you see, kind of in 1 week, we measure a large fraction of the Voyager mission, and do so. Since I showed you a really fussy launch of Voyager, I owe you less fussy launch of Webb. Before I show you that, I just want to remind you that the tip of this rocket was built in Switzerland and is protecting the spacecraft that is sitting at the top. You can hear the countdown. In this case, it's in French because it's in French Guiana in the European spaceport where that rocket went into the sky.
Standing by for terminal count.
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And
Allumage
liftoff.
UAP, décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
I still remember that launch because I was so tired and so worried. Because, of course, the investment that sat on top of that rocket was something like $8.5 billion. And the rocket had never carried anything that expensive. So that tells you I'm not the guy who was most worried. The CEO of the company was most worried because he knew that's the end of his career if something goes badly. It did not go badly. The telescope went up there and basically dropped off. The rocket went up there, dropped off the telescope. And what happened just with Voyager, it went up there and just started its journey. With Webb, what we needed to do is kind of unpack the transformer, which is that telescope. Remember, it had to fit into this tip of the rocket, which, of course, is much smaller than the size of the telescope, which I described. It's only on the inside of the rocket, it's only something like 4.5 meters. The mirror itself is 6.5, so you know it won't work other than folding it up, and certainly a tennis court doesn't fit in it either. What I did doing this, that the team had practiced this for many, many times. Actually, I decided, like normal, we always should practice how we do it. And I mean, we test as we fly, and we fly as we test. So I actually did not stand in the room except at the very end of this deployment. And I remember when, at this position that we are right now, I was on a ski lift in Utah, and I got a text that said the entire telescope is thermally unstable. Because when one of the arms came out, the telescope started losing its temperature balance. And what the team did is exactly what the movie did, immediately threw the other one out, even though that was only planned for later in the week. That also helped, immediately solved the problem, but also created a deployment that was faster than any one of the engineers predicted. This was the hardest piece of this spacecraft. What's the hardest piece of Voyager? Is to survive the long time and get back. The hardest is to actually set up the telescope here. So I want to show you some data, just like I showed before. Again, both Voyager and Webb entirely transform how we think about the universe, about our solar system. And again, in this case, with very different data system, with a lot of power that is there. This is Jupiter. That's, of course, where Voyager turned the corner. And this is Jupiter in extreme in IR, extreme IR. So what you see is whatever is bright is warm. And so you say, where is it bright? It's the polar regions. What could that be? Oh, it's northern lights. We just had northern lights last week in many parts of the world. I think by the time it was midnight here, we already lost part of it. But, you know, northern lights are also down there raining onto Jupiter because it has a strong magnetic field, just like the Earth. You see the nebula there, down there, the almost hurricane structure in the hurricane structure in the planetary surface. You see, it's warm. So there's friction that is happening as it's turning around. There's many more things you can say, like you could say, wow, there's a ring. Remember how we learned that the only planet that has rings is is Saturn. Nope, Jupiter has one too, just really faint. By the way, Uranus has one also, already discovered. So rings are quite common. Again, this also here. In this case, the ring is material that's coming out of a moon, a volcanic moon, that's just kind of just dropping sulfur in a ring, and that's what we're seeing here. So you see that all in one image that is there. This is another one. This is something like 3,500 light years away. So I told you to Voyager it takes 23 hours. This one, 3,500 years. So it's a little bit farther. We've not been there. It's still in our galaxy very cleanly. And of course, it's in our galaxy in a place where stars, in fact, die. You know, of course, that every atom in your body is at least 1 billion years old. The heavy, the kind of atoms we give each other as presents, like the rings, they're all from dying star centers, kind of neutron stars that go into each other and that explode and kind of get rid of the outermost layers. That's the brownish stuff. And then you see the light dots in the middle. Those are new stars that are formed. New stars that are formed just like our solar system. That's another view. The other one was the Eagle Nebula. This is the Carina Nebula, another one like this. Frankly, the first image we brought down of a nebula, I remember standing in front of it, and everything looked so fuzzy because my eyes were tearing up because, A, I was so grateful the damn thing worked. But more importantly, look how beautiful nature is. Nobody has ever seen nature that way since then. This is another nebula, and I told you how stars explode. You immediately see the explosion. If you looked a year later, that front out there is actually farther because it's still blasting out. In the center is the leftover core of a star, and it's going out. And on the other side of the equation is gas that is falling together. The new stars that are falling together right in the center where a new star is igniting is where planets are forming in that plane, perpendicular to the ejection over the polar regions of the stars. So what I just showed you is stars dying, stars being born, and of course, around these stars, we have planets whose atmosphere we can measure with this telescope. The way we do that is we have the big mirror, we have an occulter, so we can take out the star in the middle and just look at things on the outside. And we see in the atmosphere of this star is CO2. In this atmosphere of this planet, an exoplanet, a planet around another star, is CO2, is methane, and so forth. That's the data we're bringing down. I just want to show you only one more picture, which also is one of the first we related. It's a picture in the southern sky in this particular celestial place. And what I'm doing is I'm pulling in the camera so you see what we're observing. Just for you to get a size of that, if you take a grain of sand, put it on your stretched out arm against the sky, you can cover that square. So basically in that square, this particular one, by the way, anywhere I point, there's a lot of galaxies in that square. On this chart are about 10,000 galaxies. Behind my grain of sand that I'm stretching out on my arm. I hope you do that sometime at night and just think about it. Each one of those galaxies is about 100 billion stars. Each one of these, per star, there's at least one planet. So just imagine the amount of places out there that remain to be discovered, like Voyager did, the 6 that I told you about. So that's what I wanted to show you about this. Now let's talk quickly about the data before I close off. So basically, cloud-enabled computing and all the technologies that you're working with have transformed entirely because of the richness of data, how we do research. In 2018, when I was at NASA, I pulled all the data up into the cloud because it was really clear that this wave of AI and cloud computing is coming. And so we put it up there. We were probably late. We're still ahead of the other agencies, but still late. We put it out there. It's 200 terabyte of data, not that much still. But nonetheless, that enabled a huge speed increase of at the analysis, and basically changed the focus on just away from just focusing on new data to analyzing all data. Just like I said at the beginning, by far, Mode 2 now outranks for Code 1, Mode 1. So people analyzing all data or much different data, new data in the context of old data is very important. And what really happens now is a new revelation. If you look at kind of the new data that come out, increasingly there's novel AI tools that are really having a lot of impact. This is one example. What you can do is an entire scene of James Webb data in our own galaxy, and basically look at it in time slices, and basically train an AI and basically measure all and detect all exoplanets in that scene. That used to take something like an exoplanet per day. We can beat that by a lot now. What happens now is high schoolers are finding exoplanets because they're better at coding than some of the astrophysicists out there. So I'd encourage you to go kick some astrophysicists' rear. So I mean, it's amazing what you can do. The data are all out there, just they're up for a picking. The other one is, I told you about all these galaxies. They're kind of beautiful. But if you want to do actual statistics and science and population studies of galaxies, you need to train an AI looking at all the galaxies and their redshifts and different spectral patterns. And the vast majority of new data, new insights come from that analysis. The data in the cloud, basically with data cubes with images attached to each one of them, fully trained and analyzed. There's a telescope that's going to be launched in 2026, if Trump lets it, that basically will, in 1 month, have the same amount of data that Hubble had in 30 years. So we're bringing really big data. I just showed you Webb. The Roman Space Telescope will by 10 or 50x increase that and basically create that kind of playground for people like you. People who know how to use these tools and know how to analyze them. So as you look at the night sky, I just want to, from the ground, this is a picture from an amateur photographer. You may or may not know him. I'm giving him credit here. I just love his images. Looking at the night sky, just be aware that the reason we know about both our planetary neighbors and this galaxy and the galaxies beyond that is because of these data engines. We've built some really tiny ones and some bigger ones and even bigger ones to come. So I just absolutely am excited with what you're doing, and I hope that the technologies you're developing are very much used for many things, but including discovering the nature anew with tools that were only made out of dreams in the past. Thank you so much.
So thank you for this very thrilling insights. I wanted to ask you one question. How are you?
I'm doing fine.
I asked that question because you stated in a podcast that the most important questions in life are the short ones. Yeah. That's true, right?
Oh, they are. The short ones, I always said the importance of the question is inversely proportional to the length it takes to ask them. So many scientists, when you said, what are you working on? It's like 11 sentences. It's like, it's not important.
So what's the question that drove you the most over the past years now?
I think the question scientifically that drove me the most is really, is there life out there? So if you really look at the missions that I pushed the most, is really trying to figure out, is there life out there? And the way we're doing it is actually going to places such as the moons of Jupiter, but also going to Mars and trying to find either fossil life or life in the oceans. But then also looking with the James Webb Space Telescope at patterns of life. When life arose on Earth, the entire atmosphere changed. And so we're trying to see these changed atmospheres. Ideally, what we'd like to see is signatures from intelligent societies. We've been looking, frankly, when I was at NASA, I started programs that were not existing before, where we're looking for what we call techno-signatures as well. I think we should look at all of these. We haven't found any, but we keep looking.
And I think what you said is that keep looking and seeing like hints on life, existing life, means you have to assume that there is change all the time, right? So you assume that not what you see is the truth, but what could have been and could be is the truth.
Yeah, kind of one point I could have made stronger with this James Webb Space Telescope. What you're really seeing is your history, with a big H. So it's not your parents, your grandparents. It's where are the atoms in your body coming from? It's from all of these, not the one we're seeing here, but from a galaxy just like it that started and disappeared and a new galaxy started. And so basically everything is in a change of flux, right? Kind of sometimes we look at the night sky and we think, oh, this is nice, everything is so steady and all the same. Not the case. If you look carefully, it's all hell is going on there, and things are changing constantly. Like I was really disappointed when I realized that the Polaris, the North Star, is a variable star. That sucks, right? You think everybody looks at the Polaris, it's like, wow, that is the steady, this is how we find. No, it's variable. So it's like kind of not even that.
Was it hard to get into that mindset? Because for me, it's really hard to get there still.
So mentally, right? I mean, it's actually a broader question that you're asking, because the question is, how do you handle life? Knowing, not only in the stars, but also here, there's no such thing as a steady, comfortable thing. Like many people, they grow up and want to be in a place where they can just be steady, comfortable. I think kind of the analog of being on a boat in a lake and everything is just perfect. Like, you know what's happening tomorrow. That is an aberration. I always say life is more like a river. Like, it's always moving and kind of shit happens. Do you see kind of, it's like, why did that have to happen? Well, it's like it lined itself up. So we're moving, and kind of dealing with that change can be really stressful. So for me, kind of in my mindset, like of looking at the universe really helped me just realize this is life. Also at the small level, being able to deal with change is really what is nature. Change is the rule of nature. It's not, steady state is not.
Lovely. I don't want to take too much space here, so I want to open up for questions. Thomas has the mic. Up to you guys.
Hi, thank you very much for the talk. How was the Voyager maneuvering? It did not have thrusters, right?
The Voyager, say again?
How was it orienting itself?
Yeah, it has
thrusters.
Yeah, it has thrusters. Yeah, it has thrusters. And it also had, for a long time, it had wheels, momentum wheels that you could use. They all failed. So I mean, the good news is it's quite away from anything that perturbs it. So it has little thrusters, and they still run. Right now, the one antenna, so Voyager 1 is actually in the only place you can communicate is from the southern hemisphere on Earth. So the antenna in Australia is under construction right now. So we don't know how Voyager is for a few months. It's going to be fine, I'm sure. But usually what we do is once per year we flip it. And the reason we flip it is we're still measuring the magnetic field. In the meantime, it's the galactic magnetic field because we're on the outside of the influence of the sun. So we're in the pristine galactic magnetic field. And so to kind of subtract your own magnetic field out, you flip. And so you use the thrusters for that.
Thank you.
There's another question up here. Up there. Maybe you can throw the mic. Just disclaimer, we can't see too much of you guys because the spots are really, really...
We use my eyes.
Yeah, that's perfect.
Thank you, Matt, for this interesting talk. I was wondering, with all the pollution of the satellites we have turning around the Earth, is this an issue if you launch a new telescope up in the sky?
Okay, so first of all, the pollution of satellite, the biggest worry is about ground-based data, especially radio telescopes. Kind of if you take an optical telescope and say, if I look at a small area in the sky, how often does a spacecraft fly through it? Not very often. So if you looked at, I know the data from the Hubble Space Telescope. The Hubble Space Telescope is below most of the spacecraft now. It's on the way down. So it's at like 400 or so kilometers. 3% or so of the data we have to throw away because the spacecraft flew through. So that's with radio telescope, it's a lot harder because the radio waves are broader, right? So it's like buzzing in the ear. So you kind of have to throw away the entire period, so to say. It's harder to subtract it out. So that is affected. It's also, if you wanted to put a spacecraft in low Earth orbit, you'd have to make sure you don't bump into others. So that's actually in low Earth orbit, that's a problem. Now, why would you care about the spacecraft in low Earth orbit? Well, they're the ones who give you weather forecast, amongst other things. They're the ones who help. Remember how that landslide just went down in Bluton? So you basically say, how did we know that it's moving? Well, it's LiDAR measurements from space. They're sitting there. So the debris, or kind of the overpopulation of low Earth orbit is really a challenge for that. Every telescope I've shown you, including basically every new telescope we're doing, we're putting far away from the Earth. So they're fine. So kind of the way you should think about, by the way, it's just if you want to talk about geography in space, I talked about 1.5 million kilometers, kind of in the midnight direction. That's Lagrangian point L2. So we drop it there. And so that's kind of, think of that as the new island where we put all telescopes. So eventually we'll just put a laser communication station from there down to the Earth. That's what we're going to do. We're already working on it. So perhaps it goes through the LEO, low Earth orbit communication systems, or perhaps right down to the Earth. But we're dropping all the telescope there. They're fine. But nonetheless, of course, the problem that you're talking about is very severe, and one that we should start to work on. It's not severe enough yet for people to act now. It's one of those problems. We'll act immediately once the first few spacecraft get shot down out of orbit, especially if they're military spacecraft. That will help.
So you are concerned of sustainability in terms of Earth and space, right? So it's part of the ETH program, as far as I know.
Absolutely.
Is it like forward-looking, like the sustainability from now to then? Or is it also part of the program to think about what is already out there and shouldn't be out there?
Oh, it needs to be both. Right? Kind of the only way to inform yourself about what's happening in the future is to understand how you got there. So for me, you want to understand climate, you need to understand how we got there. Yeah. And so for me, it's really, I'm a data-driven guy. So models are good, but data are better. Yeah. So I want data that got us there. So yes, we're looking really carefully at that. By the way, sustainability, just so you know how important and kind of how new this is, 3 days ago in Nature, a paper came out that talked about that the launch rate that China, the US, Europe, and everybody predicts in 2030 will take 10% of the ozone out of the Earth. So, I don't know whether that's correct, that paper, right? You know the science process. You put it out, you do the analysis, then you shoot at it, try to figure out what it... But that got my attention. One of the authors is from ETH. Okay. So he sent it to me 4 times, so it was hard to not... To overlook it. I'm glad he did that, by the way. It's an important paper. So sustainability is something that's with us, and we need to be careful. It also means how, for example, how we fuel rockets. That's what that means, but also, how we allocate resources such as low Earth orbit.
Very, very interesting. I think there were more questions.
Thanks for the excellent and very interesting talk. I was wondering, what's your favorite answer to Fermi's paradox? So the question, where is everyone in the universe? Why haven't we never detected any sign of a civilization in the universe?
I think, I'm not convinced there's a Fermi's paradox yet. Let me tell you why. So if you looked at the scale of the galaxy and said how many stars are kind of in shells, remember the speed of light is the relevant speed. Basically say, when was the first time humanity as an intelligent society was observable? The answer was probably in the 30s or 40s, right? So if you look at how far are we observable, it's a pretty small fraction of our galaxy. So if you look at that and basically say, again, you need to go both ways, like how many options did we have? It's just not many yet. So it could be that there is a true paradox, but I think the paradox also comes from an assertion that kind of things are in steady state. And I know that question because we went the other way. How many places can we actually observe techno signatures and so forth? Now, that assumes that the physics is the way we think it is. So in other words, Einstein, when he was in Zurich and in Bern special relativity, Zurich general relativity, which is super successful theory. We use it all the time practically. You use it. Your GPS has a relativity correction. If that is correct, there's really no shortcut. There may be a shortcut, like these wormholes that you see inside, but that means the theory of relativity, any relativity, breaks down. So that's my favorite one is we just haven't been around long enough. So if you turn it the other way and basically say, like, okay, so how many intelligent civilizations are in our own galaxy? Drake's equation says that the last factor, the question, how many stars are there, how many planets per stars, how many livable planets? The first three we've measured now. By the way, the number 2 and 3, we only measured the last decade. So there's still 4 factors to go. And the last factor is the one I want to point to is tau, time. So the question is, how long is an intelligent civilization observable? And that's the big question that goes back to sustainability, right? So kind of like, is there a self-destructive kind of character from civilization that have gotten rid of all their competition? So I gave you the first answer of the Fermi paradox. I don't think there is one because we haven't been observable. If you want the second one, the second most likely is there's just not many around because if they're there, they kill themselves up. And the third one is what others are saying. Perhaps we're the only intelligent life in all of our galaxy, which would put a lot of responsibility on us, I would say. I don't think if you did a group of astrophysicists this way and you voted, many people would probably go with the first answer, not the third one. But remember, science is not a democratic activity. So it's either right or wrong.
Hi, thank you so much for the talk. I've been a big fan of NASA since I was a child, and now I'm wondering how worried should I be about its future given the new administration? Do you have any thoughts there? Also, its science projects in particular.
Yeah, so I've been struggling with that. I've been in a bad mood since I saw that budget, and I started giving interviews, and I'm going to go in 2 weeks to Capitol Hill and giving a talk about it. So I'm engaging myself because if there's anything I know about kind of risks, is you deal with them, even if you're not sure how important they are. So I think we all should focus on it. What I'm going to do is mostly meet with Republicans, because they need to do their job. And of course, so does the industry as a whole. I just literally today, I was with a CEO of a big aerospace company in Geneva, and I basically told them I need you to speak about NASA science programs. You have no right being in this industry if you don't support that. That's the industry that got you where you are, so you need to talk about it. So we all should take it really seriously. My hope is that this insane budget is going to get rejected, just like it was when I was there. Of course, I worked through the entire Trump administration the first time. It was not as bad, but we had cuts in science also. The first budgets looked really bad. Not as bad as this one, by the way, but it also looked bad, and I just want to tell you what happened. The 4 years of Trump was the biggest increase of science ever in the history of NASA. And the reason for that is people pushed against it and said, this is a good investment for the nation. I don't know whether that will be the case. I want to only make one more point. And the first time I saw the budget, the first person I called is the director of the European Space Agency and said, this is your opportunity to kick ass. And I just want to tell you, yesterday, I'm not going to announce it officially, but yesterday I hired the top system engineer in the top engineering house in the US, and he's coming to ETH.
Thank you.
I mean, I want to attract the talent. It's an opportunity. We need to see it also as an opportunity, and actually, we should be doing these things too, right here, and we can do them. And so for me, yes, we want to fight the other thing, but for God's sake, let's build this stuff ourselves.
Is there anyone else with a question? We have one?
Thomas.
Thanks for the talk. I think it's very inspiring that the Voyager 1 has been there our whole lives and it's still, working. Are we still learning new things and getting new science from that tiny amount of data?
Yeah, I've asked that question, and I was in charge of it. And I was convinced at that point we are. So kind of the 2 or 3 things we're still doing. Actually, the turbulent level in the interstellar magnetic field tells you a lot about its history and its composition. And the structure is really, it's like if you looked at the turbulence level of a lake with very, very little wind. So you need to look for a long time until you see the waves. So kind of measuring the magnetic fields is one of those things where you can put a limit on something that's absolutely not observable. There's other events that are observed and have been observed until recently, which are when galactic perturbations hit the Earth heliosphere on the outside. So the influence range of the sun, there's radio waves that are emitted. So those radio waves have been observed and kind of with spatial, because we have 2 spacecraft with triangulation. So we actually, if you want, can see our sphere of influence of the sun from the outside. And so basically we've gotten statistics from that. Of course, we want to turn it around and use it to also observe places like that in our own galaxy, that underneath which are planets like ours. So there's some interesting things. The vast majority of learning is behind us, let's just face it. Short of somebody saying, it's flying up to an alien, that would be cool. But, short of that, frankly, it is one of the most important missions ever done, even if it died today. And so for me, we're just going to try to keep going. I think as a humanity, there's a lot of people who tried to cancel it. Nobody was successful so far. There's always the one person who reads sci-fi and basically single-handedly turns the switch, so, yeah.
Perfect. Any more questions? We have one more.
It's like an IT question maybe. So thinking about Voyager, you said it takes ages to get an answer back. How do you test like a fix for a problem? Do you have like computer models? Do you have like hardware that is identical that you can test?
So, frankly, I've been amazed. We had so many problems with the spacecraft. You cannot believe it. It's like every time I tried to prepare everybody as maybe the last one. I went to Congress, look, we lost it again. And what we do have is basically we don't have the circuits anymore, but the circuits are simple. So yes, we have models of the circuits that we built. Again, they're not hard because they're so simple. We have models of the circuits that we've built, and we have a team that we had it's now the 4th generation of engineers that really learned how to run these things. So what's happening is whenever there's a hiccup there's modeling going on. Until the guy who managed Voyager, he is like 85 and still comes in from time to time. So it's like, how did you build that? And he remembers stuff. That's all he remembers, by the way, the old stuff. But John is just an amazing guy. So the team really wants to do it. It's models of the circuits and a lot of just ingenuity and kind of case study kind of analysis that they're going through. And then you basically take your heart in your hand and just try. Send some command and cross your fingers and see 50 hours later, did the right thing happen? And sometimes it takes like a month until the right thing happens, and then all of a sudden we have it back. Like, holy cow, it doesn't want to die. Yeah.
It's amazing to think of it like in economic mindset, like if we have clients and they ask us for a change, and like, okay, I'll try. You have an answer in 50 days, maybe 60.
Exactly right. But Voyager has a better excuse than you, right?
Always, like always.
So the speed of light is hard to beat, So, yeah.
Okay, perfect. Any more questions? So there is one more hand. Thank you.
Thank you very much. How optimistic are you about the future of science? Because a few years ago, the best minds were working for NASA. Nowadays, the best minds are selling you shit.
Yeah. People want to clap for that, yeah. Look, I think science in many ways is very deeply human. Kind of go hang out with a child and you understand that asking questions about nature is something that is deeply within us. By the way, there's a lot of brain science that shows that exploration and so is kind of innate to who we are as humans. So I think that's who we are. I do think kind of the science apparatus that has built, frankly, has shifted away from humans in ways. So you can be critical of the budget proposals that are there. Sometimes these are symptoms that people no longer kind of appreciate what we're trying to do. So I think kind of when I talk about the optimism of the future of science, I always say that's our job, to do a better job talking about it, to do a better job motivating it when those of us who are scientists or are in science careers. But kind of realistically, I think the next decade or so, it may get worse before it gets better. Like I just really believe, and part of it, as I said, is self-inflicted. We cannot drift away from people. And kind of, I just want to tell you, right, kind of take climate science. I talked to some climate scientist who was really derogatory about farmers. And I basically said, have you ever talked to a farmer? They're the easiest people to understand nature. Like I understand that they have a hard time with policies that kind of they think threaten their economic existence and so forth. But the thing is, if you cannot talk to farmers about science, there's something wrong. Why do I know? I grew up next to farmers. It helps to grow up in Heiligenschwendi for some things. Like I knew it's not hard to talk to farmers about science. It really isn't. You just have to realize they look at nature themselves. They observe it very accurately. They're interested in it. You can't show like up with 20 equations and drop them on the table in the bar, right? That's not, by the way, most people get scared away by that, except you, most of you. But my point is, we need to learn that. We need to take it as a challenge. And frankly, we have to get some of the best people into science. My hope is with the revolution that relates to data and genetics, there I see kind of super talent going into that. That will help us for medicine. There's many other domains where that has happened in space, kind of exploration. Many of the top people went into it with the commercial revolution that happened there. So actually the best people went there again. But if we really talk about science itself, I'm with you. We have to. There are some challenges that we need to face and get through it. I'm not worried in the long run, or I would be worried about the existence itself of us as a human race, because I think it's so intrinsically linked.
I think you said like something, the beauty of science is to question all the things constantly, even though we assume that we know something for sure. So I think that's what we can contribute to science. Never stop asking questions. Even though we think we know something, we might ask another question, get behind it. And I think that's maybe a good closing word for you to close your speech, for us to close this day. And I would love to see Thomas and Philip on stage to close this, this evening with us.
Huge round of applause.
Thank you. That's it now. Perfect.